All right, welcome to day one, the exponential, logistic, and logarithmic functions chapter. So we're going to be doing this flipped classroom business. So this is the first video. Hope that you like it and hope I'm not too awkward. So let's get right into it. So we'll start off with the basic form of an exponential function is right here, which is not drawing. There we go. All right, so we got f of x equals a times b to the x. So exponential function, basically x is in the exponent. So we're just going to explore a little bit of this. And we're just going to do this first example 1 here. So if you feel like you know how to do this, you can skip this example and go to the next part in the video. So if I'm doing f of 4, that means that I'm doing 2 to the 4th power. Remember, I'm just letting x equal 4. And let's see, so that's 2 times 2 times 2 times 2, so that's 16. Then I have f of 0, so that's going to be 2 to the 0 power, and remember that anything to the 0 power is 1. Next I have 2 to the negative 3, so we have to remember what negative exponents do. So a negative exponent is going to kind of rewrite this like that, and then we can simplify that as 1 over 8. And last we have the fractional exponents. Okay, so those are the trickier ones. I think I'll start writing up here because I might need to write a lot. So I'll start off with getting rid of the negative exponent by rewriting it in its fraction form. Next, so this 3 over 2. So the 3 stays as an exponent, and the 2 kind of, it becomes the root. So it goes in the kickstand of the root symbol. So if I rewrite this, it's going to be 1 over 2 in the kickstand, which I don't need to write, right? If we don't write it, it just means it's a square root anyway. And then 2 to the 3rd. So let's see, that's 1 over the square root of 8, which I can simplify just a little bit more. I can say that's 1 over 2 rad 2, and I'm not going to bother rationalizing it. So hopefully you kind of remember how to deal with exponents, positives, negatives, fractions, all of that fun stuff. All right, so what we want to be able to do here is to take a table of values or even a graph and kind of create this a times b to the x equation. So we have this very general equation going on over here where basically when x is 0, so we just figured out this, that when if we did b to the 0 power, it's going to be 1. So whenever x is 0, we're going to know what the a value is. Okay? And then all the exponential function says is that each time I'm going to multiply by the b value. So we can use this pattern to help us figure things out. So over here, if I'm looking at g of x, okay, so when x is 0, I know that a is going to equal 4. And for h of x, I know that a is going to equal 8. So what I really need to do is just figure out, well, what's happening each time. So each time that we move from one x value to the next, okay, I'm multiplying by 3. All right? And over here, I'm dividing by 4, but we can't really do division by 4. So we write it as the multiplication equivalent of that, which is going to be 1/4. Okay? So now I can write what g of x is. So g of x is going to equal the a value, 4, times the b value, raised to the x power. We get the same exact idea for h of x. It's going to equal a times our b value, raised to the x. Okay? So now I'm just going to do an example of this. If you feel like you kind of get it, you can skip this part. So let's think here. Let me get this up a little bit higher on the screen. So we got the data representing population. Use the data and assume the growth is exponential. We want to figure out when will this population surpass 1 million. So one of the things that we typically do with years in a table is that we'll actually let 1990 equal t equals 0, and then we'll let 2000 be t equals 10. You actually could let t equal 1, and then your time intervals would be 10 years, but it's easier for most of us to think about this if we let each year actually be a year. So what I can do then is this is going to end up being my A value. Okay? So I have my population is going to equal A times B to the t. So I'll use t instead of x because we're talking about time here. And just to kind of emphasize that this is really the A value, I'll have the population is 782,248 equals A times B raised to the 0 power, because t equals 0 in 1990. So that's going to give me b to the first, so now I officially know what the A value is. So what I really want to figure out next is, well, what is the B value? So I'll actually use this point to help me figure out the B value. So I'll have 895,193 equals my A value, which is 782,248, times B raised to the 10th power, because now t is 10. And what I can do is use my calculator to kind of help me out, because these are big numbers. I can't do them in my head. So I'm going to divide both sides by this number. Okay, so that's going to give me b to the 10th equals like approximately I don't know, some numbers like that. And then all I'm going to do is take the 10th root. Now some of you maybe don't remember how to take the 10th root, so I'm going to jump over to the calculator and do these numbers for real over there. So here we got our calculator, and let's see here, where are the numbers? So I'm going to take 8, 9, 5, this is fun, right? 9, 3 divided by 782,248. That gives me that. So that's what b to the 10th equals. So what I want to do is first hit the number 10. I'm going to go to math. And then you can see right here, number 5, there's this little X in the kickstand. So my 10 is going to fill in where that is, and then I want the answer that I just took. Okay, so now I know that that's what b is approximately. So it's approximately 1.01. All right, so b is approximately 1.01. And what this question is asking me is, when is this going to surpass 1 million? Okay, so if my equation is now, roughly this, I feel like I'm going a little too slow in this video, so I might start picking it up a little bit. Let's see, so we have 1 million is going to equal my p-value, and I'm trying to solve for the t value. Okay, and we don't know how to do that right now, officially. So what we have to do is actually graph this. All right. So in order for me to be super accurate, I'm actually going to store this value as b, because that's what it is. And now I'll jump up into my graph, and I'm going to do 1 million. 1, 2, 3. That's 1 million, I think. And then my other equation, so 782,248 times b raised to the x power, and I'm going to graph these. So I'm going to do zoom fit, because I think that'll show me a nice intersection of them, at least I'm hoping. There's my 1 million all the way at the top of the screen. Not particularly helpful, but hopefully I will see this. I'm not going to. So I need to change my window. I need to, let's see, I don't need negative time. I need to see a little bit further into the future, so I'm going to go 25 years into the future, and then I'm going to do just kind of hyper focus around this 1 million. So I'm just going to go on either end of it. Okay, so there's my 1 million, is dead center. Now I'm hoping my graph will show me this intersection as it does the next one, or this will be good. Woo! All right, so I'm just going to hit second calc and intersect, hit my enter 3 times, and it gives me this. 18.2 is when this is going to happen. All right, so I'm going to jump back to our notes over here. Let's get the marker the right size. So I got calc graph, so I'm showing my work of how I got my answer. And I got that t equals 18 point something or other, I forgot what it was already, 0.2-ish. Now remember that t is the year since 1990. Okay, so I can actually just do plus 1990, and that will tell me what year this is, which is approximately 2008. So the population is going to surpass 1 million sometime during 2008. Woo. Alrighty, let's go to the next page. All right. So, exponential growth, which we're going to see when we do the graphs in the next lesson, it's unrestricted. It just keeps getting bigger and bigger and bigger and bigger and bigger. But that's actually not really realistic in all scenarios, because there are some times where it's a limit to the growth. Like you can't let it grow any bigger. So if I were to take like in science class and have like a little petri dish and have little like bacteria growing in here, like there's a limit to how much they can grow, because eventually they're going to reach the edge of the petri dish and they can't grow anymore. So what we want to do is basically come up with a different equation that would model this, and this is called the logistic function. So here's the basic format of a logistic function. We have two main ones. So we have this one that kind of just uses A, B's, and C's, and then this one uses that mathematical number E, which I think I talk about on the next page or tomorrow, who knows, but don't worry about it right this second. So, in this function, there's some cool things that go on. In particular, this right here, super important. This top number, that's how big this fraction can get. So we call that the limit to growth. So in our petri dish, however big this petri dish was, that would end up defining how big our C value was. Okay? Now, the most basic version of all of these up here is when we have these A, C's, and K values equal to 1. Okay, so we get this really basic, the basic formula right here. All right? And even though it has an e to the x, so you might think that it's exponential, there's actually no way to obtain e to the x by using translations, reflections, horizontal and vertical stretches and shrinks. So it's a whole new class of functions, even though it kind of resembles an equation, the exponential one. So we'll do an example using this, so if you feel like you got it, you can try the example on your own and skip this part of the video. So we have population of deer after t years is modeled by this function. So we want to know what is the initial population of deer. Okay, so I'm just going to do p of 0. So if I plug this in, okay, I'm going to get 1 plus 90 e to the, essentially the 0 power. So that's 1001 over 1 plus 90. Okay, so I'm going to jump over and use my calculator because I can't do that type of math in my head. I don't know if you can. So I'm going to do 1001 divided by the 91. Okay, so 11. Cool, so the initial population of deer is 11. Yay! Now this next one's a little bit trickier. It says when will the population be 600? So that's writing this equation. So 600 equals 1001 over 1 plus 90 e to the negative 0.2t. And I'm trying to solve for t. We don't know how to do this algebraically yet, so this is another one where I need to jump to the calculator and graph it. So I'll clear out those values. I'll put in my, what am I looking for, 600. In this equation I have 1001 divided by, and you have to be really careful here. I need to make sure I have parentheses around the rest of this. So I'm going to do 1 plus 90. E is either right here over the division or over this ln. Doesn't really matter which one you use. This was a negative 0.2x. And I'm going to kind of guess what I think it is. Okay, so I'm going to leave this 25. I think that's a pretty good guess. My y, min, and max, well, I'm looking at when is the deer going to be 600. So I'm going to let the minimum just be 0 and the maximum be like, I don't know, 1100. And that should put that line pretty close to the middle of my graph. And now I'm hoping that I'll kind of see this. I don't know if I went far enough out. Oof. Just made it. Okay, so I'm just going to do our second trace calc, do the intersection. I was lucky and I just got it on screen. So 24 years. So if we jump back to the question, 24.5. So when will the deer be this population? They didn't give us any sort of initial time, so we can just say in however long that was, I already forgot, 24.5 years. So approximately 24.5 years. All right. Now this last question is actually really easy to do. What is the maximum number of deer population that's possible in this park? That's this. Ooh, as I move the entire thing, I don't know how I managed to do that. That's that number right there that I just half crossed out. The maximum number of deer, according to this model, is the top number, 1001. No math required. Done. You having fun yet? All right. Good, good, good. So, I hope you enjoyed that lengthy pause right there. I don't know what that was. I'm probably not going to edit it out. So, just embrace the awkwardness. I know I am. Let's see. Population P, changed in constant percentage rate. We want to find a model that represents this population rate. So, all we're going to do right now is create a different type of population model. So that's slightly different than the one we were just using, which is y equals a times b to the t, as I move the entire thing again. We're just going to come up with a different one. So if I start off with my initial population of 0, I'm just going to write that as p with a little sub-zero because it's easier to write. And if I want to find how much the population has changed using this percentage rate r, well then it's going to be take the original population and then multiply that original population by r, and if you add that together, then that's your new population. And what we can do is actually factor out this p0, and I'm left with a 1 plus r. And what I'm going to refer to this as is p sub 1. So for year 2, I'm going to do the exact same thing. I'm going to take p sub 1, and I'm going to multiply it by r, and I can again factor out a p1, which is a 1 plus r, and I'll get that. But P1 is something I can rewrite in terms of P0 and 1 and r. So I can actually say that this is P0, 1 plus r, times another 1 plus r. That got really messy really quick. So if I just summarize that super quick, that's a P0, and then I have a 1 plus r twice. Okay? I hope you're starting to recognize a pattern here. So that's what I'm going to call P2. So over here, got P2 plus P2 times r. That will be the population after year 3. You can do this similar idea here, right? I can say P2 is going to be factored out, and I'm left with an extra 1 plus r. This is what P2 really is, so I can rewrite this as P0, 1 plus r squared times this extra 1 plus r. So now I have P0, 1 plus r to the third. And I think that we probably have our pattern now, right? P3 is P0, 1 plus r to the third. So if I'm doing this one right here, which I'll use a different color so we can actually see it, I'm going to say P0 times 1 plus r to the t, whatever t is. Okay? And formally defined right underneath. We should have just read it. We wouldn't have had to do any of that work. So we got our initial population, we got our rate is how much it's changing, and then t is in years right now. If your rate is greater than 0, your population is going to be increasing, so we call this a growth factor. If your rate is less than 0, then your population is decreasing. We call this a decay factor. The main types of questions you have are right here. You have this radioactive decay, which is oftentimes taking the form of this second bullet point, which is actually called half-life. Okay? And then we also have this maximum sustainable population. So we just actually did one of these on the previous example. But these are the main types of questions that you might come up with. So I'm going to do this half-life model real quick, and we'll see if we can get a nice fun-filled answer right here. So let's think here. Suppose the half-life. So what that means is that our rate is going to be 1/2. We're going to be shrinking the size of our population, whatever that population is, in half. And so this turn, our population is this radioactive substance. This 20 days is really important. We're going to use that in a little bit. And there's 5 grams present initially. We want to figure out when will there be 1 gram. So I'm going to start off with my radioactive substance. Okay, I have 5 of it original, so that's my initial population. I have 1, and then because it's decreasing, I'm going to do minus my r value. Okay, now I'm going to put an x value here, but we're going to end up changing that after I just simplify this a little bit because it's annoying to keep writing it like that. So I'm going to say 1/2 to the x. Now x is how often this half-life occurs. And the problem is that we have this kind of special value going on up here, which is that we need the half-life to only happen every 20 days. So I need to slow this exponent down right here, because if x equals 1, I don't want it to take the half-life yet. But if x were to equal 20, then I want it to take the half-life. So the easiest way to accomplish this is to actually just divide this exponent by the length of the half-life. Because now, when x equals 20, I'm going to get 1 there, and it will take the 1 half-life. And when x equals 40, I'll get 2 in the exponents. It will take 2 half-lives. You kind of see how that works? Now I can just jump over and actually solve the question. So I'll jump way over here, and I'll say I'm looking for when is the radioactive substance going to have 1 left. So I'm going to get 1 equals 5 times 1/2 x over 20. And again, we don't know how to do this yet algebraically. We will eventually, so I'm just going to run over and graph this in this fancy little calculator we got going on over here. So clear this stuff out. I'm going to put 1. I'm going to put 5 times 0.5. See if that will work. Raised to the x divided by 20. Up, and I missed the x. All right. I'm going to play with my window here. So I have no idea how big the x value should be. I'm just going to guess that. So I could kind of figure this out, right, a little bit. If I take 5 and I cut it in half, I'm going to get 2.5. If I cut 2.5, I'm going to get 1.25. If I take that and cut it in half, I'll get a number. So I need at least 2 or more half-lives. So I'm going to do 60 because that's 3 half-lives. And my y values, I started off with 5. So this should give me a pretty decent window. I'm hoping that there's our thing. See how it's decreasing over time? Okay, that's our decay. That's because we did minus 0.5. And now I can just do second calc, intersect, enter, enter, enter. So I can see after 46 days, there will be 1 gram left. All right, so let's summarize that. So after 46 days, woo, do a pretty little box around it or whatever you do, good to go. All right, I think that I have just a couple of additional examples here. So if you'd like to, you can listen to these. If you feel like you know what you're doing, you can go on and basically your homework's done. But I'm going to just quickly go over these examples, completely optional. Do not feel like you have to listen to them. So let's think here. Bacteria culture, initial population 10,000. Population is declining to 6,000 in 4 hours. We want to figure out what will it be after 6 hours. So I'm going to use the a times b to the x equation for no particular reason other than I don't really care what the rate is, that r value. So right, I could use this model, and that would work perfectly fine. These equations are identical. The a and the p are equal. The b is equal to the 1 plus r. So they're actually equal. I don't really need to treat them as anything different, so I'll just kind of use them when I feel like I need to know that r value specifically, and if I don't need to know that r value, then I'm probably going to use the a times b. So I have an initial population of 10,000. That's going to be a. So I start off with y equals 10,000 times b to the x. Next, I'm just going to use these points that they gave me, which is that the population is 6,000 when 4 hours has gone by. Divide by 10,000, that's going to give me this 0.6, I'm pretty positive. That equals b to the 4th. Then I'm going to say b equals the 4th root of 0.6. I'm not even going to bother figuring out what that number is yet. I'm just going to rewrite this over here. So this is my equation. Y equals 10,000, the 4th root of 0.6 to the x. So if I want to actually answer the question now, which is, what will it be after 6 hours? Well, I'm just going to take this exact equation, and I'm going to let x equal 6. And I can just type this right in my calculator. So type it in the calculator, I get approximately 47, ignore that decimal point, 0.58-ish. And we can't really have 0.58 of a bacteria. So what we have to try to decide is which way to round on this. all right? So our population is decreasing. So, trying to think here. Population is decreasing, right? So the graph is kind of going like this. I know you don't know the graph yet. And at 6 hours, okay, we're at that y value. I think we actually need to round up. So our answer is going to be 4648 because we haven't fully lost that last bacteria yet. Bacterium or something like that, right? I don't know how to spell. Probably way wrong. All right, so I hope that example wasn't too terrible. These next ones are really just thought-provoking ones. I don't think we're actually going to be doing a whole ton of math on them. In fact, I don't think we're doing any math. Let's think here. We've got a table, f of x, g of x. We have 3 equations over here, and what we're trying to do is figure out, well, which one do we think represents f of x, and which one do you think represents g of x? So the first thing I'm going to look at here is kind of what the rate of change is going on between these things. So all my x values are going up by 0.5. So if my f of x or g of x values are going up by a constant rate each time, then they might be this y2 here, because that looks like it's a straight line, and straight lines have slopes that are consistent throughout their entire domain. So let's see here. Right here, this one lost 0.10, and here we did not lose 0.10. So I know that this one can't be linear. Same thing's happening over here. We're losing a different amount, okay? So I'm pretty sure that this one can't be linear either. So I'm going to say neither of these, f of x or g of x, is going to be y2. Next I'm going to look at is kind of how fast they're growing or shrinking here. So if I look at f of x, it starts off at 5.5 and it ends at 5.05. G of x starts at 7 and ends at 0.7. Okay, so there's a much greater decrease for g of x from start to finish than there is for f of x. So if I look over at y3 and y1, they're both decreasing as I'm moving from left to right, but y3 is decreasing much more. Okay, if I look at kind of like its start value to where its end value, that's a much bigger increase than y1's. So that lets me think that f of x is going to be y1, and that g of x is going to be y to the third. And basically, explaining your choices is what I essentially just did out loud, right? That the change over time for g of x is much more rapid than f of x, and since y3 is decreasing at a faster rate than y1, it makes sense that g of x has to be y3. All right, I think that was the last one, right? Woo! All right, so we made it. I hope that this wasn't too terrible for you, and if you're still listening at this point, I don't know. Hopefully you listen to it on double speed. Alrighty. Peace out, Cub Scout.